Okay, so today we're shooting this for Friday's lesson. However, it is currently Sunday for me because I did have my second job after school on Friday, so I was unable to film this on Friday. If you missed Friday, I apologize for being a little bit late, but try to get it in so you still have the weekend to look over this, catch up on your notes, and get everything ready to go. Today we're doing linear functions. One of the big things that we're going to be defining in this section is recognizing, we're doing like site-based recognition. What is a linear function? How do I tell it from either the graph, from the equations, or from the tables of values? Like, how do I know whether or not this is going to be linear or not? If not, we're going to start moving into the graphing so we can start looking at other things about the graph. But the number one thing is just like recognizing words of shapes way back when in elementary school, you know the fact that the word CIRCLE represents circle. You don't need to actually see a circle. We're going to start moving in that direction in the language of Algebra 1. You know, how do I know whether or not things are linear? From the obvious to the not so obvious to something that we're going to show over here in a minute because it's on the other board. As of right now, a linear function is a graph that is a straight, non-vertical line. Now, one of the things that I mentioned to the students was we recognize that a linear function is going to be a straight line. Duh, it's a linear. It's a line. But what does it mean about non-vertical? Well, the idea of non-vertical is if I have a graph, pretty much every student, when I said, hey, is this a straight non-vertical line? Yes. Is this a straight non-vertical line? Yes. Is this a straight non-vertical line? Yes. 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 What makes these different than that? Well, it's the key word for function. If you remember the fact the other day when we did the lesson on how do we define if there's something as a function, if there is cause and effect, that's kind of at the heart of what we want to study. Is there something that we can adjust, something that we can edit slightly to get a different outcome? That's what we're trying to find here. This does not pass the vertical line test. Here I have a cause and effect that is very steep. As I move over, one variable increases, so does the other. One variable increases, the other kind of does. One variable increases, the other doesn't. This line, one variable increases, the other decreases. This one, as one increases, the other decreases much more so. This one, bloop, bloop. It came and it's gone. There is no cause, there is no effect. So that's the reason why we want it to be a non-vertical line. A nonlinear function is anything that is continuously curved or connected. Now, later on in a much later course, you're going to cover differentiable functions, and that's what we're going to kind of look at. And we're going to get into those, but that's several courses after this. It's not really an Algebra 1 thing. But what we're looking at right now is a nonlinear function is anything that is continuously curved or connected. The connected part, we're going to change that later on, but again, not in Algebra 1. So if I have a graph, anything that is continuously curved or connected, I could have something that is whoosh, 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 whoosh. This is continuously curved. I can have something that is just like one continuous curve, or simply for Algebra 1, we're also going to call a nonlinear function anything that is continuously connected. Boop, 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 even if they're hard adjustments. Those hard adjustments, though, are going to present problems when we start differentiating functions, but again, years down the road, so don't worry about that. The big thing that we're trying to avoid is what we call gaps, jumps, holes. So again, just working on our site-based vocabulary, like I recognize that something is wrong with this graph if there is a gap. What does that mean? That means the graph starts, it stops, and then it continues later on. I have a gap between them. So for this range, I can't pass nor fail the vertical line test because there is no cause, there is no effect. There is no recorded measurements. Gaps, we don't like. The other thing that we don't like are jumps. That basically means if I were to take these, and let's say I start here, and then I all of a sudden jump up in value, so I'm not overlapping and there's no gaps, but I'm like doodle 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 doo, and then all of a sudden, boop, I'm up here and continue forward. So that's what we call a jump. That's going to, again, present problems in a much later lesson. And then the last one, which we'll actually see a teeny tiny bit of in this course, but much more towards the end of the year, is what we call a hole in a graph. That means that you have something that's going on like this, and it looks continuous. But if you zoom in, we introduce what we call a hole, like right there. There's also asymptotes, but visually we can tell that asymptotes are broken. A hole is when we remove a single point in a graph due to something that is in the underlying mathematics of the equation, and we'll see about those in a later course. That one's going to be one that we'll cover in Algebra 1. The other two are beyond this, beyond the scope of this course, more of an Algebra 2 thing or maybe even a pre-calculus thing. But now that we've kind of covered the secondary information, let's take a look at what we're supposed to learn today. We're going to visually say, what makes this a linear function? And in the beginning, it's quite simple. Is this a straight, non-vertical line? The answer is no. Is it continuously curved or connected? Yes, so this is non-linear. As easy as that. Is this a straight, non-vertical line? Yes, okay? So this is going to be a linear function. Both these are functions. There's no gaps, jumps, or holes. This one's continuously curved. This one is a straight non-vertical line. That's what we're going to be trying to do without having to graph everything. Now, at the very, very end of this lesson, we are going to be graphing them. Let's say, I don't know how to read these tables, or I forgot how to read the tables. Well, how about I turn them into a graph, and then I can say, oh, I can see this. So we're going to cover several different ways to do this information here. But at the core of everything today, does it make a curvy, wiggly, non-straight line, or does it make a straight line? As long as it's not vertical. That's it. Okay. So when I look at the data, the first thing I'm going to look at is I'm going to say, hey, let's check the spacing on the x's. Are they evenly spaced? The answer is yes. Every time my x goes up by 1. That means, how did we phrase this in class? We said the change in x is constant at 1. So I'm going to say the change in x is constant at 1. Likewise, even if they're not continuing, like let's take a brief foreshadowing into number 4. Now, the change here is not 1, but I'm going up by 3 each time. So every time I see I went from 3 to 6, I went up. 6 to 9, I went up. 9 to 12, I went up. But I went up by 3, 3, 3. Is that constant? Yes. So it doesn't need to be 1 like this, where I'm going up by 1 each time. As long as it's a constant value, we're happy. So this says the change in x is constant at 3. Now, we'll cover in later lessons what happens if they're not constant. Right now, we're just checking very, very simple ideas. Let's make sure the change in x is always constant. Now, we're going to introduce our second Greek letter. So far, most of you know one Greek letter, and that's going to be our pi value. So pi, the 2 bars, a little squiggle on top, is going to be represented by 3.141592 as you go down your calculator. That's all that I remember because I memorized my calculator when I was in high school because I was that kid. The second Greek letter that we're going to learn is going to be about change. And when we say the change is constant within x, we call that delta x. We're going to say delta x equals 1. The change in x equals 1 every single time. Kind of like right here. The change in x is 3 every single time, so we say delta x equals 3. Now, if you remember your Greek letters, this is a capital delta. It looks like a triangle. So what we have is we have capital delta, and we have lowercase delta. Kind of looks like a D. They both make the D noise. And an easy way to remember it is we live on the coast. Where do you see, or where have you heard the term delta before? Probably a river delta, right? You have a river that flows towards the coast. Here's our coast. And over time, what ends up happening is that river will slowly floop, 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 floop. It ends up making this series of branches that keep going over each other. You know, every so often it gets a big branch, but the idea is that it wiggles back and forth across the terrain over several hundred or several thousand years. And lo and behold, you know what shape that makes? Yes, sirree, that makes a triangle. So therefore, the big delta in math we call big change over big time. Later on in math, when the change, we don't want to look at such a big scale. This took hundreds, if not thousands, or maybe even millions of years. When we want to look at something like a smaller change, let's say the rate of change between now and now, or how about between now and now? In calculus, you're going to get to the point where that snap is going to happen so quickly, so rapidly, that you're not really going to be able to measure it. And one of the two fundamental things that you study in calculus is what happens if I assume that change doesn't exist and I'm looking at the change of a single point. Can I find the rate of change when there is only one point of data? We call that little delta. That means I've taken this and I've zoomed in on it so closely. So little change over little time, big change over big time. So easy way to remember that. If we're looking at the rate of change, it's going to be big delta. Later on in calculus, when we're looking at little change, it's little delta. But in essence, that's all we're looking at right now. I see that the rate of change is constant at x equals 1. Now I can look at the important part. Now I can see whether or not this is going to represent a linear function or a nonlinear function by the other piece of data. When I look at this, I see from 7 to 12, I'm going up, 12 to 17, up, and 17 to 22, up. I went up by 5, up by 5, up by 5. So again, I'm going to say the change in y is constant at 1. No, not 1. The change in y is constant at 5. We just said that. So that means delta y equals 5. So I can have the change in whatever variable I'm measuring. The change in x was 1. The change in y was 5. When I look at this one, I notice that my change is going down, 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 down. This went down by 6, and so did the other two. So my change in y is constant at -6, which means every time I move over, I'm going down by 6. So my delta y is equal to -6. Now, we'll cover what these two things mean because I haven't written an answer yet. I've just written something that's going to help me get to the answer. Now, what are we going to do? Because a lot of students are like, okay, this is a lot of writing. How am I going to show my work on my homework? Well, all you need to do is be able to identify from 1 to 3.5, what did we go up by? We went up by 2.5. From 3.5 to 6, what did we go up by? 2.5. From 6 to 8.5, we went up by 2.5. So all you need to write is you need to write this. Delta x equals 2.5. That's it. You don't need to show the rate of change. I think it helps, though, if you're struggling to figure out this part, write what it is every single time. Because if any one of these changes, there is no delta x. And then if I look at the y's, all I need to do is say, hey, I went up, I went up, I went up. Notice what's different here? I went up by 7, I went up by 11, and went up by 15. So right here, there is no delta y because, again, I got a different rate of change. So don't get lazy. A lot of students will just look at the first rate of change and assume that that's it for everything. We always check every data point. So here, the delta y is not constant because I have a set of 7, 11, and 15. Remember, these are the brackets where you're like right, left, or left, right, left, left, down, left, right, down, right. We're doing those kind of brackets right there. So this is all they need to show. Change in x, change in y. If it's not constant, show the three things that are not constant about it. So what does all this mean for our answer? Well, on a line, every time I move over an x, I move up. So like this one, I move over an x by 1, up and y by 2. Over and 1, up and y by 2. Over and 1, up and y by 2. Which means the rates of change have to be constant for both variables. So both of these tables represent linear functions. So this one is linear, and this one is linear. Okay? But on this one, as I move over, the rate of change is slightly different. So what that means is that the graph is bending in some way, shape, or form. I don't exactly know how. I'll actually cover this type of graph in a later date. But in this case, all we're focused on is it's not a constant rate of change consistent among both variables. So we're going to call this one non-linear. Now, again, if you're watching or you see something where you're like, hold on, pause. What happens if I just skip one? That would give me a non-constant rate of change. But like if I skipped this 630, I would go from 3 to 9. That would be a 6, and this would be a 3. That'd mean I go down by 12 and down by 6. Would that not change the answer, but keep the table of values as a linear function? Yes, you're correct. We're going to cover that in a later date. So what happens if we're missing data or the change in x is not constant? The change in x is not constant. We're going to cover that when we deal with slope, and we'll answer those questions right now. Or not right now, later. As of right now, that's going to be it for this part. Take a quick pause. I'm going to move the camera over to the other board, and we'll get started in the second half. Okay, so we're on the second half now. Now, what happens if I have an equation? Now, most of this chapter is being about how do I turn equations like this into graphs, or turn equations like this into the tables that we just did and then into graphs. But in the very, very beginning, we can recognize some of the ones and say, hey, what type of shape are these equations going to make? And most of us remember at this point the one equation of a line that we've all done, and that is y equals mx plus b. Now the m represents the slope, the b represents the y-intercept, but in essence, any form of these lines like y equals 2x minus 6 is one example. Now pay attention, this is a linear function. What's different about this versus some of the ones over there? Well, if we look at both the y and the x term, the y has an invisible 1 as a coefficient. The x in this case has a 2, but it doesn't really matter as long as it's a number. We're not really concerned with the number. Let's call this a 1, and then I see the 2. Both of those are being multiplied by their variable. I don't see anything else. Addition, subtraction, we're ignoring it. I'm just looking at the terms. The y's and the x's aren't being squared, they aren't being rooted, they aren't being absolute valued, they aren't being exponentiated, they aren't being tertiated. There's nothing going on with those values other than multiplication. That's it. So we can immediately look at an equation and say, if the only thing going on is multiplication, it is a linear function. If there's anything else, it's nonlinear. And then we'll cover all those different types of nonlinear on the second part of this course. But right now, all we care about, is it a line or is it not a line? That's it. So when I look at number 6, I see I have a negative x minus y. Well, both of these terms, I see that there is an invisible 1 and an invisible 1. They're both being multiplied, which means that I could rearrange this equation into this shape. Now, you don't need to do this, but this is what we could do. So if I want it to possibly look like y equals mx plus b, I could rework it. I could say, okay, 0 equals negative x minus y. I could add the x. Actually, no, I want to move the y over there. Let me add the y to both sides. That gives me a y equals negative x. Boom, that is in y equals mx plus b format. So all I need to do is look at it and say, only multiplication? That means that this graph is a linear function. I don't need to do this. For number 7, my x has a square root. No matter what I do to that equation, I'm not going to be able to get it into y equals mx plus b format. Something else is being done to my x value, which means this is a nonlinear function. We don't care what shape it makes at this point. Later on we will. All we care about right now is it's not a line. My x is in the exponent position. Again, that's something different. So this is a nonlinear function. We'll cover this in January, but again, as of right now, we just say this isn't a line. Right here, I could rearrange this by saying, hey, y equals negative 1 plus x. I could just swap the order of these two and say y equals x minus 1. That's in y equals mx plus b format. But I don't need to do that. All I need to do is look at it and say, hey, I see my x, I see my y. Nothing's being done to them other than multiplying by a 1, multiplying by the invisible 1. So therefore, this is going to be a linear function. My next one, I have an absolute value bracket. That's something different, nonlinear. We might actually do this one at the end of this chapter. It might be at the end of the next chapter. We're going to see this one pop up real shortly. But as of right now, we're just like, that's not a line. We don't like that. Here, the exponent, or the x has its own exponent. It is squared. Again, we're like, hey, that's something different. This is not a straight line. We'll actually cover this in, I think, either chapter 8 or chapter 9. This is a quadratic, if you remember your number 1 from earlier in the lesson. But again, all you're doing is you're looking at the equations and saying, is there something weird going on with the x or the y? That's not a line because we haven't seen those yet. So the last half is we're going to move into graphing. So we want to be able to build a table of values given the equation. Let's say it's the second half of this course, which is why we're building the skill. And I want to see what shapes these make. I want to pull out different features of these graphs. Well, I have to graph them. And graphing them just presents a much better secondary description of the graph than trying to pull everything out abstractly like this. So we want to be able to graph things. So I told the students, I was like, today was the day that we needed to have those graph papers out. So if you're watching this video, have graph paper with you for the future because we're going to be doing a lot of graphing lessons. Algebra 1 is all about graphs. We graph all day, every day. Have a pack of graph paper. They're like $5. It'll last you the year. You can split it with a friend. That'll last you the entire year. But after this point, anything where we have to actually graph it, we can't sketch it on notebook paper. It's not going to be good enough for what we're doing. For the questions in the homework have to be graphed on graph paper. Well, let's go ahead and take a peek at this. When we're graphing something like this, I'm not making you choose the x values yet. I'm not making you plug them in yet. I gave you the x values, and I've already plugged them in myself and gotten you the y values. So you don't need to do anything other than just graph these values. So if we're just graphing these values, I need to figure out how far to the left and the right I need to move. Well, here I need to move 2 to the left and 4 to the right. So one of the things that I like to do is if I'm moving 2 to the left, I'm going to give myself at least 3 boxes. So on the graph paper, your graph paper is going to look like this. Now, for some reason, when students graph, they waste like no space, and they'll put the graph like right there, right beside their table. And I'm like, okay, cool. Conservative space action there. So if I need to move 2 spots to the left, I'll give myself 1, 2, 3 boxes, and then I'll draw my vertical line. Okay. That gives me 3 spaces. I should have enough to move around right beside my table of values. Now, I'm only moving 4 spaces to the right, so I'll block that off here in a moment. My y values, I need to go at max down 4. I have no positive values. So if I have no positive values, what I'm going to do is I'm going to give myself 1 positive space. Okay? So that's my graph so far. Now the other thing that I see students do, this is perfectly fine. If you want to, you can draw every graph right in the center of like some arbitrary space. That's okay. This is what I see most students do though. And a lot of students take it a step further and they're like super conservative on the paper. They're like, I only want to go down 4. So 1, 2, 3, 4. I say, okay, give yourself a 5th space. So at minimum, stop right there. You can make the graph bigger than it needs to be, but it can't be any smaller than that. I need to go 4 to the right. 1, 2, 3, 4. At minimum, it needs to be this big. So that's the smallest graph that you can make. You can make it bigger, that's perfectly fine, but that's as small as it can be. Next thing we're going to do is I'm going to label my x and my y axis. X tells us left and right, y tells us up and down. And then remember, the x values tell you your left and right directions. Your y values tell you your up and down directions. So negative x means left, positive x means right. Negative y means down, positive y means up. So it's literally just a series of directions to get to the point. -2, -4 means left 2, down 4. Start at the cross section of where the x and y axis meet, which we call the origin. That's where we start counting for everything. So at the origin, I go left 2, 1, 2, down 4, 1, 2, 3, 4. I'm not counting boxes, I'm counting the lines in between the boxes. Because I had a couple students today that they were counting the boxes and they would go 1, 2 boxes, 1, 2, 3, 4 boxes, and their point would be right here because they were counting boxes. We're not doing that. We're counting the spaces between. We're counting the lines. It looks like there's boxes. We're really counting the lines. Okay. My next point is at 0, -3. I always go back to the origin. Pretty much every class got that. I only had a few outliers where some of the students were like, oh, I start counting from here. No. Always go back to the origin to follow your directions. So go back home and then say, okay, 1, 2, 3, down. This one says go back home, go to the right, 1, 2, go down 2, 1, 2. And then go back home, go forward to the right, 1, 2, 3, 4, down 1. Now, the test for today is, we're talking about, is this a linear function? If I were to try and draw a straight line, would it actually be a straight line? And so let's see if I can draw a straight line on this, which is why we need graph paper and not a sketch, because if there is a little bit of deviancy, we need to be able to see it. So in this case, yes, I can draw myself a straight line. Now, the next thing that we want to do is I want to label on any graph, I always want to label the x and the y intercepts, where it crosses both axes. So my y-intercept, where it crosses my y-axis, is right there, and where it crosses the x-axis is right there. That would mean I actually have to extend my x-axis just a little bit. Boop, boop, boop. There we go. After I identify them, I have to label them. This one is already labeled 0, -3, and I can see that because I have a 0 in my table. I know that's going to be one of my intercepts. I don't know what that is, and again, hence the graph paper as opposed to sketching this. I need to be able to label that, and that is going to be at 6, 0. Now, some students were freaking out because they're like, well, mine doesn't cross at 6, 0. That's okay. We're not at the point where this information is important enough that we need to be able to use it. We're practicing the art of graphing so that when I need to be able to pull those points out for answers, I can use the graphs to give me those answers. Right now, we're just practicing the art of graphing. So I've got my 2 intercepts labeled. I looked at this and I said, hey, is that a straight line? And the answer is yes, this is a linear function. The last thing that a lot of students, and when I say a lot, I mean probably more than half are doing, that I wanted to point out, and I pointed out during class, is that at the end of every line, we have to draw arrows. What that means is this line continues beyond what I'm showing you. If I don't draw the arrow, what that implies, especially in geometry, is that the line stops right there. And we don't call that a line anymore. We'll either call that, if it stops here and goes on in that direction, call that a ray. And if it stops on both sides, we call that a line segment. That's part of a line, doesn't keep going. So we always, always, always draw arrows when we want to say, hey, I could keep drawing, I could keep drawing, I could keep drawing, but I didn't. So, feels pretty good about that one. Let's try another one. So again, I'm going to leave my graph a little bit over here because I'm not super conservative with my space. Have a little bit of room to move around. This I need to move 1 to the left and 8 to the right. So at minimum, if I'm moving 1 to the left, I'm going to give myself 2 spaces. Foop, foop. I need to move 5 up and 3 down. I'm going to round that up to the next number. In this case, it's actually down to the next greater negative, so -3. So if I need to move 5 up, I'll give myself 1, 2, 3, 4, 5, 6 spaces. I'm going to start right there. I need to go 8, 9 spaces beyond. I'm going to give myself 1 extra. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Label X and Y. And then just follow the directions. Now notice, one of the things that you see right here is you see a 0, which tells us that's going to be one of my intercepts, either my X or my Y. How do I tell which one? Well, my Y has a 0, which means it's going to have a height of 0. This is going to be my X-intercept. So I'm going to make sure to remember to label that one. But as of right now, go to the origin, go left 1 line, up 5 lines. Left 1, 1, 2, 3, 4, 5. There's my first point. I'm going to go back to the origin, right 2, up 2 and a half. Here I'm going to go back to the origin and write 5. Back to the origin, go right 8, 1, 2, 3, 4, 5, 6, 7, 8, down 2 and a half, 1, 2 and a half lines. And again, I'm going to see, can I, which is why the graphing paper is required on this, can I draw a straight line? If this was a sketch, I might not know if this was a straight line or it might be slightly curved. Okay? If I still haven't convinced you yet, what if your point was
right here, would you think that maybe your sketch was a little bit off and you're like, no, that's a line, I didn't graph very well? That's why we want graph paper, because this would actually not be a linear function if that point was even slightly over. So we want to be as exact as possible. Okay. The next thing that we're going to do is I'm going to label my intercepts. I have an intercept here, which we already knew about, 5, 0. And I have an intercept up here. Now, it's not actually at a point, which again is one of the things that we want to get in the art of practicing. If your point isn't exactly there, don't freak out right now. Relax. This is about practicing to make sure you're doing a little better. Are your points where they should be? Did you miscount? Are you not using a straight edge? Do you need to go buy a ruler so that you can trace these points? What exactly are we not doing to where our point is slightly above? It's like 0, 4.1, maybe 4.2. So if you're not exactly there, it's not a big deal right now. Just kind of look at what are you doing, maybe where we need to improve upon that a little bit. But otherwise, when I look at this, what type of function do we see? Linear. So then I challenged the students and I said, hey, how about you do number 14 completely on your own? They tried it. A lot of them did really well, like really well. Some of them really struggled because they were still struggling. They don't know where to start. They don't know how to draw the lines. So I want you to take a moment, pause, and try it on your own and see how you do. Okay. I'm now going to continue on, assuming that you have paused and tried this. Let's do it together now. Okay. So my x needs to go left 2 and right 2. So I'm going to give myself 3 spaces on both sides. I need to be able to up 4. These are all positive values. I don't have any negatives. So I'm going to give myself 5 spaces. 1, 2, 3, 4, 5. So my line's going to go right there. And that'll give me 5 spaces up. Now again, at minimum, if I need to go right 2, I'm going to give myself 3 spaces. So there's my x, there's my y. Again, you can make these graphs as big as you want. That's the smallest you should be going. Actually, you could probably get away with not even doing that part down there. If you're like, well, there's no negatives, Mr. Johnson. Okay, cool. No negatives. Give yourself 1 space for a negative. I go left 2, up 4. 1, 2, 1, 2, 3, 4. Go back to the origin. Left 1, up 1. That's at the origin. So remember, when I see zeros in my table, those are my intercepts. Right 1, up 1. Go back to the origin. Right 1, up 1. Right 2, up 4, back to the origin, right 2, up 4, and then I connect them. Can't do a straight line. So what I'm going to do is I'm going to connect it with a smooth curve, just like that, a smooth curve. I notice the fact that this is already, I know my answer is going to be nonlinear. But I'm going to go ahead, I'm going to label all of my intercepts. So I'm going to circle this point and label it as 0, 0. Bingo. So how'd you do? That's at this point, and again, this section is all about graphing nonlinear versus linear functions, recognizing which is which. That's all we're going to do. We'll actually spend time graphing stuff like this. This is a quadratic, for those of you wanting to know. We'll cover that in chapters 8 and 9. But for your homework over the weekend, let's do it right here. Your homework for 3.3 is going to be, it's on pages 121 and 122, so page 121 through 122. Basically what I'm going to do when I do stuff like this is I just write down page 121. If it goes on to the next page, I'm assuming that you're going to be able to flip the page. I've actually had students that struggle with that, where they'll stop at the end of 121. They're like, you didn't tell me to do page 122? I know the problems were over there, but you said 121. I'm going to assume that you know if it goes on to the next page, go on to the next page. You have numbers 1 through 10 odd. Now, those were like the questions we did on the other board, identifying graphs and identifying tables. You have 15 through 22 odd. That's like this. They're all like this right here. Just look and identify. And then we have numbers 25 through 28 all. Now I know this feels like a lot. Remember, this is identifying graphs and tables. The tables, I think there's 2 of them, might take you just a second, but the idea is that you should flow through this less than 2 or 3 minutes. This is like the equations. This whole section should take about 1.5 minutes. So we're up to about 3 or 4 minutes right now. This is the graphs. This is where we should spend probably about 1.5 minutes to 2 minutes on each one. So all in all, we're looking at probably about 10, 11 minutes there. Again, I'm not trying to be overwhelming. I want to make sure that we're trying to do about 10 minutes or less, but let's make sure we get those 4 graphs done. We have a weekend. And this will be due on 10/6, which is Monday. So due 10/6, which is Monday. That being that, I will see you guys tomorrow, even though this video is going to be posted as though it's Friday. I'll see you tomorrow on Monday.